Welcome everyone to Harvard CMSA Quantum Matter in Math and Physics seminar series. We are very delighted to invite Pok Man Tam from Penn. He will be speaking about his recent work with Clausen and Charlie Ken on topology of Fermi C. Let me remind the audience, please feel free to interact with Pok Man and ask questions during his talk. Let's welcome Pok Man, please.
Thank you very much. Thank you, Juven, for the introduction. Can you hear me clearly? Just to make sure? Great, thank you. So good morning, and maybe good afternoon and good evening to everyone, because I know this seminar series that Juven helps to organize is quite an international one. So it's really my great honor and pleasure to be able to speak to a broad, distinguished audience here. So today I'd like to tell you a little story about metal. It's about ordinary metal, not Dirac or Weil semi-metals, which are more traditionally known as topological. I'm really going to talk about common metals like copper, or maybe to some of you, silver and gold also is quite common to your daily life. So I'm going to talk about them. They're not considered topological from the traditional perspective, but hopefully in this talk, by the end of this talk, I will convince you that there are some topological perspectives that is actually also quite experimentally relevant. Another title of my talk would be to count holes in the Fermi sea without diving in. So I hope this question will also become clear in a second, what I mean by counting holes in the Fermi sea, and what I mean by doing that without diving into the Fermi sea. So what I'm talking about is based on these two works. This one is published already in PRX. It came out around April this year. And this archive preprint came out more recently, so it's about a month ago. So this little recent paper is about an experimental setup that we proposed that can measure topology of Fermi C in 2D using what we believe to be quite an accessible experimental setup. So hopefully I will tell you more about that in my second part. But just to put us on the same level, put ourselves in the same context, let us just quickly review what important role that topology has played in condensed matter. There are basically like two big main themes in modern days condensed matter physics. One is about topological band theory, another thing about topological order when strong electronic interaction kicks in. In one sentence, allow me to presumptuously summarize it. I want to say these are phenomena related to the topology of the wave function. So for example, in SSH model in 1D or in integer quantum Hall effect in 2D, it is really how the quantum wave function, the block wave function twists when you go around the Brillouin zone that determines some robust quantized properties of the system. For example, the number of gapless boundary modes that you can find on the boundary of your integer quantum Hall insulator, that is determined by the Chern number, which is determined by how the block wave function twist in the Brillouin zone as characterized by the integral of the Berry curvature. And that again is related, we know is very well related to quantized response such as Hall conductivity. When strong electronic interaction kicks in, we have the notion of topological order as introduced by Professor Xiaogang Wan. And this applies to many systems such as fractional quantum Hall states, quantum spin liquid states. And again, if you look at the many-body wave function, then you can see how the excitations, anionic excitations, have fractional braiding statistics, which again is related to some physical consequences, such as a ground state degeneracy that is topological. It depends on how you put your system onto a spatial manifold. Depending on the topology of the spatial manifold, your ground state would have a degeneracy that depends on the genus of your closed surface. And this again is related to gapless excitations, quantized response, and all these has the origin in the topology of the wave function. Some of the audience here, I know, have contributed to both of the subjects, but allow me today to switch gear to talk about something slightly different, because today I'm not going to focus so much on the topology of the wave function. And many of the examples that I talked about here, they are gapped systems. And today I'm not going to talk about gapped systems at all. I'm going to focus on a very common, ordinary gapless systems, metal, which has a gapless Fermi surface of gapless excitations. So this actually evade many traditional way of associating topological invariant to the system. If you have a field band, then you can associate maybe Chern number or Z2 index to each occupied field band. But when you have a gapless systems, you can't quite do that and associate a topological invariant to describe such systems. So you may wonder whether there are any topological response or any topological properties in the gapless systems as ordinary as metal. And that is something I want to focus on today. And turns out there is topology that we can talk about. Because the metal, and every metal, is characterized by a Fermi sea that is surrounded by a Fermi surface. If you view it as a geometrical object, then you can talk about the structure of holes on this manifold being the Fermi sea. And nature actually gives us a variety of topology to speak of. For example, if you look at a 2D, say you have a graphene, it comes with two Dirac cones, one at K and one at K prime point. But let me focus on just one Dirac cone, and a Dirac cone, and dope it with electrons or dope it with holes. Then you get two different Fermi sea topology. So let me move the window a little bit away so that I can look at this figure here. So you can see if you dope the graphene with electrons, for each Dirac cone, you get an electron-like Fermi pocket that looks like this. Quite simple, right? If you dope it with holes, then you will get a hole-like Fermi pocket that look like this. So here I'm drawing this square as the Brillouin zone, and a green shaded region corresponds to the Fermi sea. These are the regions in momentum space which are occupied by electrons. These has two different topology because in the electron pocket you can draw cycles or loops that they are all trivial, but they can be contracted to a point. In a hole-like Fermi pocket, you can draw cycles that are non-trivial. For example, if you draw this cycle, okay, because these two boundaries of the Brillouin zone, they're identified to each other. So this line is actually a cycle, is a loop, and this loop cannot be contracted to a point. This actually corresponds to the loop on a torus. It's a non-trivial cycle. You also have this non-trivial cycles. So the hole-like Fermi pocket is a Fermi sea of a different topology than electron-like Fermi pockets. So that happens quite naturally in two-dimensional electronic systems. In three-dimensional electronic systems, you get more exotic things. For example, so in sodium and potassium, these are the more mundane situations where the Fermi sea looks like a ball. It's really like the ideal Fermi gas. So the topology is a ball. But if you look at something like copper or silver or gold, these commonly occurring metals has a Fermi sea that is quite large, that the boundary, the Fermi surface actually touches the boundary of the Brillouin zone. And because the Brillouin zone has periodicity, and when this Fermi surface touch the boundary of the Brillouin zone, your Fermi sea actually get exotic connectivity in it. So it turns out if you look at copper and silver and draw out how the Fermi sea looks like, it actually looks like a donut with 4 holes instead of like in sodium or potassium, the Fermi sea looks like a ball. So the topology of Fermi sea in copper and in sodium or potassium, they are very different. So a natural question occurs. If we can speak of this drastically different topology of the Fermi sea in metals, are there any physical quantities that distinguish different types of metals from each other? Are there anything robust that one can actually probe in ordinary metals? So that is the question that we'd like to ask. And in this talk, in the 2 works that I'm going to introduce to you, we partially answer these questions with some pretty interesting answers. So another way I like to formulate this question is, how can we count holes in the Fermi sea? So to probe the topology of the Fermi sea without diving in, because just as von Klitzing, he did this experiment of measuring quantized hole conductance and seeing these plateaus that characterize different topological phases of quantum Hall insulators. He didn't have to do a quantum tomography or to probe the quantum wave function in the quantum Hall system and see how it twists in the Brillouin zone, and then he calculated the Chern number. He didn't have to do that. What he did is to measure an elegant, simple physical quantity, a Hall conductance, and then see this very perfectly quantized plateaus, which reflects the topology of his system of the integer quantum Hall insulator. So we want to ask a similar question here for metals. If the metals has different topology in it that's associated to the Fermi sea, can we indirectly probe this quantized integer? So that is the goal of our talk, and there will the two parts in which I explain how we kind of achieve that. In the first part, I will talk about how we can use a multi-point density correlation at equal time to probe the Fermi C topology. And that can be in turn related to a multipartite number correlation. So by multipartite, I mean you will cut your system into several pieces. And by cutting it, I don't really mean using a knife and cut your metal into several pieces. I mean an imaginary cut, just as how you would do to calculate entanglement, bipartite entanglement entropy. But here we need to go beyond bipartite entanglement. We have to talk about multipartite entanglement. So if you look at number correlation in a multi-partition systems, or look at the mutual information that characterizes the entanglement, we will argue that you can actually probe the Fermi C topology in momentum space by considering a multi-partitioning in real space. So that is summarized in our first paper. And then in the second part, I will try to tell you a more experimental and practical way to probe the Fermi C topology in 2D. That makes use of a Josephson pi junction. So you have a 2D electron gas that you want to probe. It has a Fermi C and you want to know its topology. You can proximatize it with two superconductors with a pi phase difference, and then there will be Andreev states localized at the pi junction. If you do a transport experiment making use of these Andreev states, and by that I don't mean measuring Josephson current, because Josephson current corresponds to current flowing in this direction. And when you have a pi junction, you really don't have a Josephson current. But you have Andreev states localized at the junction that actually moves along the junction in this direction. What we demonstrate is that if you do a transport experiment using these Andreev states and try to do a transport experiment along the junction, you can actually probe the topology of the Fermi C in a two-dimensional electron gas. And that has a pretty interesting rectification effect that generalizes the one that you see in diode. And it is topological because it's related to the Fermi C topology. So I think this is also quite neat, and I'll hopefully convince you how that can happen. But to begin, let me first define more clearly what is the quantity that I want to measure that is associated to the topology of the Fermi C. And that is a very simple quantity that I think we all learned when we first learned topology, which is the Euler characteristic. So Euler, actually mathematicians even before him, tried to characterize the surface of convex polyhedron, and this quantity is being introduced. So if you look at the convex polyhedron and count the number of vertices and label it as V, and count the number of edges and count the number of faces, and you add and subtract them in this way, what Euler and his peers found was that this always gives you number 2 if you do this counting for a convex polyhedron. And actually, if you do this counting for any graphs, and by graphs I mean it's a bunch of edges and connected together so that you can talk about vertices, edges, and faces, anything that can be put onto the surface of a sphere will always give you this counting too. And if it's a graph that can be embedded on a torus or a genus 2 torus or a genus G torus, that this counting will give you 2 minus 2G. So that is presumably the first topological invariant being introduced into mathematics. And in modern days, one can actually associate an Euler characteristic to not just a graph, not just something with a triangulation, but actually to any topological space in arbitrary dimensions in terms of this alternated sum of Betti numbers. So BL here, I'm denoting the Lth Betti numbers. 0th Betti number actually counts the number of connected components in this topological space, and the Lth Betti numbers counts the number, the classes of L-dimensional holes in this topological space. I'm going to give some example on the next page. But basically, for any topological space, one can generally associate an Euler characteristic to this space. And in this talk, topological space that we're going to focus on is the Fermi C, which is defined by it's a space in the it is a manifold in the momentum space defined by the occupied electrons in the metals. So we're going to probe this Euler characteristic that I'm going to denote as chi f, and we hope to probe it. Let me give you some examples in various dimensions. So if you have a one-dimensional metal, just as the one that I illustrated here in this figure, and this plot, so you have a dispersion E as a function of K. If I put my chemical potential here, then your Fermi C will be composed of two disjoint intervals in momentum space. In this case, the B0, the the 0th Betti number that counts the number of connected components would be 2, because you have 2 components of Fermi C. And that's it, because B1, B2, B3, all higher order Betti numbers, they are all 0. So the order characteristic for 1D would be just counting the 0th Betti number. So in this case, it would be 2. If you move your chemical potential just a little bit, then you're not going to change this number until you undergo a Lifshitz transition. Your chemical potential crosses a critical point in this energy dispersion and become this, for example. Then B0 will become 1. And you have 1 component of the Fermi C. In this case, the order characteristic is 1. And you may ask, is there a case where actually you would actually need to involve B1 in 1D? There is a situation, and that's when you have an insulator. When you have an insulator, it is like completely filling a band. So your Fermi C actually extends across the whole Brillouin zone in 1D. And the 1D Brillouin zone has the form of a circle, is a 1 torus that has a B1 equals to 1. Sorry, I think there's some noise outside. I hope it's not disturbing you too much. But in this case, okay, B0 is 1 and B1 is also 1. So for a field band in 1D, the order characteristic is actually 0, because B0 and B1 cancel out with each other. And that actually extends to higher dimensions. For 2 torus, for 3 torus, the order characteristic is 0. And so if you have many bands and many of them are filled, they just contribute an insulating part in your metal. They don't contribute order characteristic. So we're only considering the conducting bands. They will contribute a non-zero order characteristic. In 2D, so in 2D now we have to involve B0 and B1 in general, even when you don't have a completely filled band, even when you have just a Fermi surface like this electron pockets or hole pockets, you also have to involve both B0 and B1. For example, now you can see when you have an electron pocket, the order character is +1, because B0 equals to 1, you have 1 component. B1 equals to 0, because any cycles can be contracted to a point. There are no non-trivial cycles. And so chi F equals to +1 for each electron pocket. For each hole pocket, you can draw 2 non-trivial cycles. And so B1 equals to 2. And so the order characteristic equals to -1 for each hole pocket. In general, when you have some numbers of electron pockets and some number of hole pockets, the order characteristic for the Fermi C in 2D equals to the difference of these 2 numbers. Okay, I can give you many more examples in higher dimensions, but let me am I going to get a question somehow, Juven?
Yeah, since you recommend me to ask. So let me just make sure, you mentioned the 1D example, you can also get B1. And
yes.
In that case, are you saying the whole Brillouin zone are filled?
Yes.
And in that case, you will get what's the full Euler characteristic for the system?
So for in 1D, if you have a filled band, then B1 is non-zero. B1 is actually 1. Then by definition of the order characteristic, it is B0 minus B1, which equals to 0, because both B0 and B1 equals to 1 for each field band. When you have a field band, you have 1 component of field band, but that 1 component of field band also gives you 1 class of non-contractible cycles. So both B0 and B1 equals to 1. And so the order characteristic for a field band is 0.
Okay, but
is that clear?
That's fine. But suppose I have the field bands such that some of the bands, you may just imagine like some region like what you draw in your top figure. Suppose the Fermi level is almost at the top, where you might think there are several distinct subpieces of the field subband, but perhaps just increase slightly the chemical potential, you may feel the full band. Is there some kind of a consistency condition between the situation we're saying? Just slightly feel above or below the
this
let's say just your figure. Suppose the EF is basically somewhere near you may say the saddle point.
Is it basically where I'm drawing here? If you can see my pointer.
So you might
this corresponds to the case where you have a topological transition, actually, because your Fermi C topology actually changes at this point. because this corresponds to a case where these two intervals actually merges into one. At this point, chi-f would change suddenly from 2 to 1. We don't have a theory to describe this transition. What I'm going to talk about in the rest of my talk would corresponds to cases that are far away from this transition, in which case I can talk about the chi-f. Yeah,
I think there's something like a Morse theory describe this type of things, right?
Yes. Actually, if you look at E of k as a height function, a Morse function, then this point actually corresponds to a critical point in your Morse function. So crossing it actually corresponds to a transition. Yeah, because in Morse theory, you'll be doing some counting using critical points, and the critical points that are covered by your height function. And here you cover 2 critical points. Here you actually cover 3. They have opposite signs because one is a minimum, 2 are minimum points, 1 is maximum points. So you can also use a Morse theory counting and get the Euler characteristic. And the situation that you were trying to focus on corresponds to a little bit ill-defined case, because you're just going to cover 1 more critical point. And at that point, I don't know how to calculate the Euler characteristic because it's actually at a transition point. It is a little bit like in a topological band theory case. This is actually analogous to the situation where you're closing a band gap. Yeah.
Oh, thanks.
Okay. Welcome. So, okay, in 3D, then you can also do this counting, or you can invoke a relation between the Euler characteristic of a boundary, which I denote as this chi partial f. So f is my Fermi sea, and partial f is the boundary of the Fermi sea, which is the Fermi surface. It is a 2-dimensional closed surface. You can invoke a relation between that Euler characteristic and the Euler characteristic of the bulk. They are related by a factor of 2 in odd dimension. So in particular, in 3D, we know that the boundary will be a 2D closed manifold, and we have this well-known formula, 2 minus 2g. So you can use this to calculate the Fermi sea Euler characteristic. It's basically 1 minus the genus. So for example, when you have copper, if you recall a few slides ago, copper or sodium or gold, its Fermi surface form a donut with 4 holes, so G equals to 4. The Fermi sea Euler characteristic would be 1 minus 4, which is minus 3. Okay? So with these examples, I just want to convince you that naturally occurring in our nature, there are metals with Fermi sea topology whose Euler characteristic actually runs over different integers. And since we really have a wide variety of topological invariants that can be associated to the Fermi sea topology in metals, we want to ask the question whether they play a big role or whether they can be measured. If they can be measured, and furthermore, if we can demonstrate that some robustness of it, for example, in the presence of interaction from a liquid interaction, then this will be pretty cool because we can use this number to classify topologically different metals. Okay, so you can say one obvious way to measure chi-f would be to do the quantum oscillation measurement. And that is how people knew about the shape of the Fermi sea, or the shape of Fermi surface in copper or in gold or silver. The pictures that I showed you a few slides ago, they were kind of measured like 50 or 70, 50, 60 years ago. So that is a direct way of measuring chi-f, but that is kind of like asking Professor von Klitzing to measure the quantum wave function in the quantum Hall insulator and then go ahead and calculate the Chern number. That's not how he discovered integer quantum Hall effect, and that's also not quite exactly the beauty of integer quantum Hall effect. It would be nice if you can have some simple measurable quantities that spit out this quantized, this integer topological invariant directly without going through all the jazz of doing an experiment, a quantum oscillation experiment, and map out the Fermi sea. And then even a mathematician can come and tell you, okay, because there's so many holes, then the Fermi sea topology is this or that, the Euler characteristics this or that. That is, in some sense, a less interesting way of doing things. What we want to do here is to come up with some physical quantities that directly capture this Euler characteristic, which may give rise to some robust experimental phenomena. So another way, as I said, to phrase this question is to count holes in Fermi sea without diving in. What I'm going to show in the next maybe 30 minutes is to show you that while I'm talking about a Fermi C topology, which is a manifold that lives in momentum space, you can actually probe that by doing something in real space. And that has to do with using the entanglement entropy. And we are actually motivated by several successful precedents, like the Cardi-Calabrese formula for d = 1 quantum critical system. People have known for a long time that the entanglement entropy has a finite size scaling, which I'm going to show in the next page. And there's a universal coefficient in front of the logarithmic scaling that probes the central charge. And also there's also this Levin-Wan Presskill formula that applies to 2D topological order. And actually, there are higher order generalizations of that, which allows one to use entanglement entropy to probe the quantum dimension, which is something about the anionic, robust properties about the anionic excitations. And because of these examples, it actually motivates us to also use entanglement entropy and try to probe chi f. So because of that, let me briefly introduce the idea of entanglement entropy. To calculate that, you have to cut the system into two pieces. So here I'm showing.
Can I ask one question on?
Yes.
Thank you. So this is Mila from MIT. I'm just wondering, when you say measuring chi f, I'm wondering about this motivation. Imagine if you have like a while nodes, it's pretty robust against perturbation. But if you have some slight change of the band, and then you can change the shape of the Fermi surface, and you can change the feeling. So is that also this robust against the different this feeling of the Fermi C, or is there any other reason to measure this chi f here?
Yes. So I'm going to show you that. I also have some numerical examples. It's not really directly applied to the Val semi-metal case, but you're going to see that as long as you have a finite, sized Fermi surface, when you change the chemical potential, of course, you're going to change the size of your Fermi surface. But if you're just doing it gradually or slightly, you're not going to change the Fermi C topology. And the measure, the quantum, the entanglement measure that we're going to put forward is actually not sensitive to changing the feeling. Namely, it doesn't care about the size of your Fermi surface. It only cares about the topology of your Fermi C. The Val node case that you talk about is a little bit trickier. So what I'm going to talk about would apply to the situation where you dope away from the Val node. Namely, when you dope away from the Val node, then you will really have a finite sized Fermi surface. Our theory would apply to that. But actually, if you electron doped away or hole doped away from the Val node in 3D, so you can say you get an electron pocket in 3D, or compared to a hole pocket in 3D, they actually all have the same Euler characteristic. So if you just look at the Euler characteristic and look at our theory, which applies when you have a finite size Fermi surface, then the quantities I'm going to introduce to you, it's actually not going to change on the two sides away from the critical point they talk about. And when I say critical point, I mean when you fine-tune your chemical potential to just touch the Val point, so that the Fermi surface actually disappears at an instant for that specific chemical potential. So then you can ask, what would the quantities, say the mutual information or the entanglement entropy measure that I'm going to talk about, how would that behave? I don't know. I don't have a good answer to that. I can only tell you what happened when you don't fine-tune your chemical potential such that your Fermi surface actually becomes a point. If you don't do that, then generally you will have a finite-sized Fermi surface. Then as long as you have a finite-sized Fermi surface, I don't really care about how big or how small it is until it becomes really too small for our theory to break down. Because there's going to be, because I'm going to talk about a finite-sized scaling of entanglement measures. And that actually has some dependence on some UV cutoff. When your Fermi surface is a point, then your UV cutoff, the length scale is actually infinite because your momentum scale cutoff is 0. So your length scale in real space, the cutoff is actually infinity. And that is the place where where our finite size scaling wouldn't apply. But as long as you have a finite Fermi surface, then your momentum space cutoff is finite. And in real space, you will have a cutoff that is rather small. When my system size go beyond this length scale, then our theory would work. So I hope it will become a little bit clearer to you when I really give you the formula. And maybe if it's still not clear to you, we can discuss again. Okay, great. Yeah. So here I define the entanglement entropy. You have a system that you bipartite into two parts, system A and its environment that I call B. With this density matrix for the whole system that I call rho AB, you trace out degrees of freedom in region B, you get the reduced density matrix for region A. With this rho A, you can calculate rho A, log rho A, and take the trace. That is how we define the von Neumann entanglement entropy. It characterizes the correlation between region A and its environment. What Wilczek and his colleagues found, and also later on more maybe slightly more systematically formulated by Calabrese and Cardy, is a very remarkable result that the entanglement entropy in a 1D for a gapless system actually has a finite size scaling that takes this form. L is the linear system size for region A, and it actually grows as log of L. And since, okay, inside the log, you have something that is dimensionless, so it's actually L divided by a UV cutoff little a. But the microscopic details only enters in little a. And changing little a is not going to change coefficients in front of the log. What they found is that actually that the coefficient in front of the log is a universal quantity that people call central charge that characterizes the number of low energy degrees of freedom in the system. So for example, when you have an Ising spin chain, C equals to 1/2. When you have a Luttinger liquid, C equals to 1. With this result, we can actually get a peek into why the entanglement entropy could be useful in probing Fermi C topology. Because if you take a 1D metal, maybe you can have several subbands. Here I'm showing you two subbands. My chemical potential is put here. So you have one band and another band. In the momentum space, you can see two disconnected Fermi C components. At low energy, you can actually view this as two copies of Luttinger liquids. For each Luttinger liquid, the central charge C equals to 1. So when you have n channels of Luttinger liquids, the central charge will be n. And this number n that counts the number of components of Fermi C is precisely the Euler characteristic for the 1D Fermi C. And that's why you can actually rewrite this Calabrese-Cardy formula into this following form and say that, okay, if you have a one-dimensional metal, just partitioning it into two regions that meet at a point, A and B meeting at a point, and look at how the entanglement entropy for region A scale with the system size. The coefficient in the front of the log would tell you the Euler characteristic for the 1D Fermi C. So that's a very trivial statement because it's just a reinterpretation of the Calabrese formula. But it's actually quite important because it gives us some inspiration to move up in dimension and try to use entanglement entropy to probe the Euler characteristic for high dimensional Fermi C. But the generalization is not as straightforward because we know the entanglement entropy actually has a boundary law behavior in high dimension. Actually, in one dimension, the boundary law actually tells you it doesn't scale. For fermionic system is more interesting because there's a logarithmic enhancement. But basically, for many systems, the entanglement entropy has a boundary law scaling. The intuition is very clear because we're calculating entanglement entropy, which characterizes the correlation between region A and its environment. They talk through the boundary. So particularly if you have a gapped system, then correlation is short range. They can only talk at a very localized neighborhood around the boundary. So if you have a larger boundary, then you will have a larger entanglement or correlation between region A and its environment. And this entanglement entropy should scale with the boundary or the area of the boundary that separate A and B. In fermionic system, as discovered by Klitsch and Geoff, that you have area law enhanced by the logarithm. The key thing here is that because in some sense it's still area law, the coefficients in front of the log would have some geometric dependence on the details, on the microscopic details. For example, this factor would depend on how large your boundary is, and also how large your Fermi surface is, and also how it is shaped, the curvature and many details of the Fermi surface. So that's not something that we want. Okay, Juven raised.
Thanks.
So yeah.
I think I would like to clarify one thing, just make sure I follow. I think the previous slide you try to relate the central charge by this Caudy whatever formulations compared with your Fermi C or Fermi surface type of counting, right?
Yes.
Actually, it's Fermi C, I think. So disjoint union of the Fermi C. So I think one thing maybe we should clarify is that the formula for the central charge for entanglement entropy works for interacting system.
Yes, yes.
While the picture which go beyond fermion or just quadratic fermion interaction of quadratic fermion, that type of Hamiltonian. In the case of a Fermi C Fermi surface, I think we are doing just some kind of free fermion type of analysis. Is that right? In the sense,
that's a very good point, Juven. So first of all, you're totally right.
And also another thing is that here the low lying degree of freedom near the Fermi C or Fermi surface is actually the vile fermions, I suppose. Right?
The chiral left and right moving fermions.
And they have a central charge 1, C left moving, C left right 1, C right is also 1. And there should be also some U1 degree of freedom that can act on this complex vowel fermion U1 symmetry, at least for this vowel points. So, but these are the case for the description from your approach. But I guess the formula for the entanglement entropy actually is probably more general.
Exactly. Yes.
Interacting CFT can also be not necessary even with any U1 symmetry that acts on the vowel fermions. So they could be different perspective, even though you obtain the same formula.
Yeah. So for example, you said right. For Luttinger liquid, I actually implicitly assume that you can have interaction, and the central charge C is still 1. But I also want to emphasize that when you have interaction, when you're having a Luttinger liquid, so something beyond a 1D Fermi gas, you can still talk about Fermi surface. You don't have quasi-particles because if you look at the Green's function, look at the Z, the quasi-particle residue, Z goes to 0. You have a different types of singularity in a Green's function, but you can still define Fermi surface, and then inside the Fermi surface, that is the part that I call the Fermi C. So you can still talk about that actually in Luttinger liquid, and actually I can actually even I would be tempted to even at the very end make connection to what we did to non-Fermi liquid in 2D and 3D. Even though, as you will notice, most part of my talk I will focus on Fermi gas, free fermions. But at some point I will go beyond that and try to make some speculations about non-Fermi liquid. And in non-Fermi liquid, you don't have quasi-particles, but you're still able to talk about Fermi surface because you can still see a singularity in the Green's function, and you can still talk about that. But yeah. I also see Professor Seiberg raise hands.
Not you, Seiberg. Professor Seiberg, please.
Yeah. Do you assume here that the small fluctuations of the Fermi surface are described by a conformal field theory, or is that assumption not necessary? Because the reason I ask is that the Caudy formula assumes conformal invariance.
Yes. So but I also think for free fermion, I think one can also establish this result rigorously. If I add an interaction, then maybe I will be tempted to say that I want the interaction to be not so strong, so that I can focus on maybe low energy excitations around the Fermi points. and which gives me the limit of be able to talk about conformal invariance. If I have very strong interaction in a system that I cannot really talk about linearizing around this region, and I'm also not talking about I'm not talking about non-interacting system, then I'm not sure how. I don't have a conclusive statement to say that. But if I'm talking about free fermions, then I know what the result should be. I think this is.
Well, for free fermions, we don't need Cardi. For free fermions, we don't need Cardi. We just know what the answer is.
Yes.
If you want to use the other things, and especially if you go beyond one dimension, so if you go higher in dimensions, I don't know whether it's even true that in simple examples, the fluctuations are described by a conformal field theory. And the discussion with L to the D and all that assumes some kind of scale invariance, locality, etc. All these formulas here assumes scale invariance and locality, I think.
Yeah. So you're right. Yeah. So I think this Klitsch and Joff work is for free fermion, but I also kind of recall that I think like around 2012 or something like that, Professor Kun Yang from Florida State, they have a work using multidimensional Bosonization. So to include Fermi liquid interaction and see how that correct this result. And I think their conclusion is that to leading order, you still have this result. The Fermi liquid interaction is going to add some subleading correction.
I see.
So, and I'm not going to really invoke conformal invariance for the rest of my talk. With this example, to be rigorously correct, I would like to go into the non-interacting limit, and to motivate. I'm just trying to motivate this result starting from Calabrese as a source of inspiration.
Thank you.
At the same time, I would also like to, if time allows, I will also kind of like to say that if you just add in small interactions, then Calabrese also tells us that for Luttinger liquids, you can have interaction and you still have C divided by 6. And that C is not renormalized by interaction. We also have some results that are not renormalized by Fermi liquid interaction. So it is, in that sense, it's going to be similar to Calabrese, just as you also have Luttinger liquid results that looks like the non-interacting Fermi gas results of this form.
Well, just discussing C assumes conformal invariance. Without conformal invariance, you don't know what C is.
Yes, that's true. So when I have interaction,
C is the conformal anomaly. So you need to have conformal symmetry so that you can discuss its anomaly.
Yeah. So when I talk about interacting electrons, I want to focus on the low energy theory, where I have conformal invariance, and I can you can use central charge C equals to 1 to label each channel Luttinger liquid. And also, I think since I'm interested in the finite size scaling, I can allow myself to go to really large system size. I guess it will also be acceptable to assume conformal invariance in that situation. When I talk about a continuum theory, a low energy effective theory for an interacting electron, describing it as a Luttinger liquids, then I can invoke this Cardi formula again. Do you think that it's reasonable?
In one dimensions, maybe.
In 1D,
maybe. In higher dimensions, I'm not an expert, but I'm told that that's not true.
Right. In high dimension, I'm not going to make connection to central charge at all. I'm not going to make connection to central charge at all. Yeah.
Okay.
Yeah. All right. So thanks for the question. So let me resume to this. On this page, I just want to lay out the difficulty of straightforwardly generalizing the result to high dimension, because if for fermions, Geoff and Klitsch has this results that shows the way that the entanglement entropy scale with system size, and in this case, it's for free fermions, has a non-universal dependence. This coefficient depends sensitively on the microscopic details, particularly on the shape of the Fermi surface, and that is something that we don't want to. We're not interested in finding. We want to know about the topology of the Fermi surface or the Fermi sea. So, so what can we do with that? We actually know that there are examples in higher dimension in which entanglement entropy is capable of extracting something topological. And that brings me to this very beautiful result by Kitaev and Preskill, as well as by Levin and Wen, who told us that if you look at the entanglement entropy for gap topological order, well, yeah, it has a boundary law contribution that is non-universal, but there's a subleading constant piece that doesn't scale with the system size, and it captures the topological piece of information that tells us, for example, for a billion system, this D will be counting the number of types of anyons in this system. And the way that one can extract this and canceling out or throwing away this boundary law contribution will be to consider a combination of entanglement entropy that is arranged in this way. Here I would like to call it the tripartite mutual information. This will be able to isolate out topological piece. Because, for example, if I look at, say, this boundary between A and C, this boundary would contribute to the entanglement entropy in a non-universal way. But if you calculate this combination of entanglement entropy, adding them up and subtracting in this way, this boundary appear in SA, also in SC, and in SAB and SBC, and they come with opposite signs. So the boundary law contribution, the non-universal contribution, exactly get canceled out, and that will leave us with the universal topological information. In the following, I'm going to argue that the topology of Fermi C can be extracted in a similar manner by considering some linear combinations of entanglement entropies that extracts the intrinsic entanglement between multiple regions, so that the non-universal pieces are canceled out and the topology of Fermi C will be encapsulated in that entanglement measure. So let me give you the general results that we realized. In order to probe the d-dimensional Fermi C topology, we would like to partition the real space system into d+1 pieces. We don't have to say too much about how we actually do the partitioning because there's not a very strong criterion on how we do that. All we require is that any two regions share a common plane. Say in 3D, they will share a common plane. Any three regions share a common line, and then all four regions be the point. So this kind of partitioning is quite generic. And in 3D, then you will cut your in 2D, you will cut your system into three pieces, and any two share a common line, just like this. Any two share a common line, and all three of them be the point. With this way of partitioning a d-dimensional system into d+1 pieces, then we can calculate the mutual information. For 3D, then we will calculate something like this. It is a generalization of what Levin and Wen and Kitaev and Preskill used to calculate the topological quantum dimension. But here we will consider a similar combination of entanglement entropy that characterizes the multipartite entanglement. What we found was that in 3D, if you look at this four-partite mutual information, it also has a logarithmic finite size scaling, but it's logged raised to the power 3. So it's a log of a linear system size raised to the power 3. Again, it will have a universal coefficients because the microscopic details, the little a appears inside the log, is not going to change coefficient in front of the log cube. This coefficient is indeed chi-f, which is what we are hunting for. It is, in some sense, it's like a generalization to the two-partite mutual information that I discussed a few pages ago. If you use this Calabrese-Cardi formula for calculating entanglement entropy, and you add them up in this way, you will find that the two-partite mutual information has a log to the power of 1 finite size scaling with a universal coefficient that probe the 1D Fermi C topology. In our work, we have a similar formula for 2D and 3D. The 3D formula would look like this. So this is the result. In the following, I will try to provide some more details and try to convince you why this is plausible. So for non-interacting, for free fermions, one can actually relate the entanglement entropy to the cumulants of charge fluctuation. The basic intuition is also not too hard to make sense of, because in order for region A and B to be entangled to each other, they have to talk to each other. And for a system with U1 charge conservation, the way that they talk to each other has to involve exchanging particles. So when you exchange particles, the number of particles in each subregion would fluctuate. These fluctuations would characterize the entanglement entropy. Actually, you have to involve the full counting statistics. Namely, you have to use not just say Q squared, the variance of the fluctuation. You also have to use higher order cumulants. But as long as you know all of them, then you can add them up in this way. So formally, you have a relation between the entanglement entropy and the even order cumulants with this coefficients, which is the Riemann zeta functions. So I just give out a few examples of them. With this relation, we can just calculate the cumulants for the charge fluctuation and use it to calculate the entanglement entropy and calculate the multipartite mutual information. So this brings me to talk about the calculation of the charge fluctuation, the cumulants of charge fluctuation. To calculate that, it will be sufficient if we know how the density correlation function behaves in momentum space. Now, translation invariance would require sum of momentum to be 0. So if I have, say, an m point density correlation function that depends on m momentum wave vectors, then not all of them are independent. They will be constrained by a single relation that imposes translation invariance. Rho, the density operator, is expressed in this way. So it's basically C dagger C. And because of this constraints, if you just calculate the density correlation, it will actually be proportional to a delta function that imposes this constraint. If you integrate out one of the momentum wave vector, then you will integrate out this, satisfy this translation invariant condition. What we found is that the end result is simple. The end result only depends on chi f, which is the Fermi C topology in the respective dimension, and a simple factor that is related to how the remaining independent wave vector Q are arranged in the momentum space. So for example, in 3D, this density correlation of 4-point density correlations would depend on 3 independent wave vectors. And if they form in this form that encloses a parallelogram, then this determinant of script Q is actually calculating the volume of this parallelogram. So, and this is actually a pretty cute result, and actually pretty beautiful result that is a little bit obscured in our paper, but I'd like to highlight it here because it's really the cornerstone of many other results in our paper. So if you have a density correlations, a d plus 1 point density correlations in a d-dimensional space, for small enough Q, we don't require it to be actually goes to 0. We only require it to be small enough. And I will be more specific about that requirement on the next page as I give more explanation to this. But the result is that if you look at the density correlations, it is directly probing the Fermi C topology in d dimension. So let me try to, on the next page, try to argue why this is plausible. In d equals to 1, it's actually quite easy to argue and easy to explain. If you look at d equals to 1, then I will ask you to look at a 2-point density correlation, rho Q1, rho Q2. If you do the Wick expansion, because rho is C dagger C and this is C dagger C, you can do the Wick's expansion and convert this integral of connected correlation function to this form. It's just an integral of f times f bar. Here, f is the 0 temperature Fermi-Dirac distribution. F is the Fermi distribution for electrons. F bar is the Fermi distributions for the holes. So f bar equals to 1 minus f. So each Fermi distribution is evaluated at a point in momentum space. If this point k is inside the Fermi C, then the Fermi distribution function f just give you 1. And if k plus q, this point, which you use to evaluate f bar, is outside the Fermi C, then f bar will give you 1. In other situations, f times f bar will be 0. Okay, so represent this integrand f times f bar as this little line interval in momentum space, and point k, I'm going to label it as a black dot because for this point k, you're going to use it to evaluate f, the Fermi distribution f for electrons. For this point, I'm going to use a holo circle to represent it. So this point corresponds to k plus q, at which you use to evaluate f bar. Okay, so if this point is outside the Fermi C, then f bar equals to 1. So you can see that this interval, which is representing this integrand, would only give you a non-zero contribution, in which case it would be 1, when this black dot is inside the Fermi C and this white dot is outside the Fermi C. And as long as this situation is satisfied, then no matter how you move it, you're going to pick up 1 as a contribution to your integrand. And if you put your interval all the way inside the Fermi C, then your integrand is just 0. Or if you put your interval all the way outside the Fermi C, then your integrand is also just 0. The only way that you can get a non-zero integrand is for this situation to satisfy, and there will be amount of time, Q amount of time, actually, Q absolute magnitude amount of time, and that actually represents the length of your interval. This amount of time, you will pick up 1 as a contribution to your integrand. So when you do this integral, you will pick up the length of your interval times the number of components of Fermi C that you have. Because for each component of Fermi C, you can do this little experiment in your mind and try to evaluate this integral. You'll put your interval at near the Fermi surface for each Fermi C, and then you will pick up a contribution that is Q, the magnitude of Q. So you may wonder what happens if you put this interval here. If you put this interval here, then you will just get 0. So for each component of Fermi C, you will only put your interval here near this point in order for your integral to be equals to 1. And then if you have n components in your 1D Fermi C, then you will have n times the length of your interval. Am I clear at this point for d equals to 1? So with this, I would like to jump to d equals to 2. If you look at the d, yeah.
Let me make sure. Is the top formula require the system to be fermionic? The density operator written as fermion?
Yes, because when you expand it out, then I want to evaluate this guy. F has to be a Fermi-Dirac distribution. I have to have the Fermi C in order to speak of the topology of the Fermi C. But once you allow yourself to talk about fermions, then your density correlation would reduce into this form. And when you calculate this quantity, then you're really probing the topology of the the ground states of your non-interacting fermionic system. Yeah, and this result will be exact as long as Q is not too large. Because if your Q is very large, such that this interval can actually connect to disconnected components of the Fermi C, then my argument would fail. Or if your interval is too long, longer than one of the components of your Fermi C, then okay, my argument will also fail. But as long as Q is small enough, you don't require it to be 0. As long as it's smaller than the typical size of the Fermi C, and also the typical distance between disjoint components of the Fermi C, then this result would be exact. For d equals to 2, there will be a similar argument. I wouldn't bother you with the details, but the main idea is as follows. You can turn this integral into, again, this product of Fermi-Dirac distribution functions. Some of them is f, some of them is f bar. In 1D, I can represent the integrand as a line interval. In d equals to 2, I can represent the integrand as a parallelogram. As a parallelogram, which I depicted here. Okay, so this gray circle this gray disk corresponds to the Fermi C. And this parallelogram corresponds to the integrand, where I will use to evaluate the density correlations. The rule of the game here is that if you stare at the integrand for 20 seconds, you realize that the integrand is only non-zero when the only corner of the parallelogram that is outside the Fermi C, or when the black dots is the only corner that is inside the Fermi C. So for example, in this situation, if you put a parallelogram here near the Fermi surface, then integrand will actually give you 0. If you put it here, here, or here, the integrand will always give you 0. The only place where you can pick up a non-zero contribution is, for example, in this situation. In this situation, then if you look at your parallelogram, which represents the integrand, black dot is the only point that is inside the Fermi C, and so this integrand would give you a +1 contribution. Okay. So when you do this, a similar argument, just like what I briefly presented to you for d equals to 1, you can have a similar geometric argument of doing this integral and argue that if you have, say, an electron pocket, which has an electron pocket then for each electron pocket, you're going to pick up a contribution from this integral that is equal, that is exactly equal to the area of your parallelogram. And this contribution is +1 or -1, actually depends on whether your Fermi C is an electron pocket or a hole pocket. So namely, whether this is gray or whether the outside is gray. If the outside is gray, then this parallelogram will give you a minus contributions that would add up to minus times the area of your parallelogram. The upshot is that one can actually establish rigorously and precisely that this integral will give you the area of the parallelogram spanned by Q1 and Q2 times the Euler characteristic of the Fermi C in 2D. For 3D, it's harder to give a geometric argument. Actually, in 2D, we are a little bit stretching the limits already.
But excuse me.
Yeah.
Question.
Please.
So, are these results all for free fermion systems?
Yes. So here I'm still talking about free fermions.
Yes. So, right. My question is that suppose, for example, in 3D, if you have say if the Berry curvature integral around the Fermi surface has a non-trivial number, will this change the result?
No. So here we don't have the information about the Berry curvature because so this is the density operator that I'm talking about, rho of Q. So strictly speaking, if you look at rho of Q, there will be a form factor. So it's not exactly equal to C dagger C. There will be a form factor that gives you the inner product between the block function at K plus Q and the block function at K plus Q.
Suppose you include that, well, how will the result change?
That will give a higher order correction. So because when Q is small, then that inner product, the form factor is actually very, very close to 1. The Berry connection or Berry curvature contribution actually comes when you Taylor expand that form factor as a function of Q, right? So if you look at the leading order, what I demonstrated here is that you will get a, say in D dimension, you will get a Q to the power of D contribution. The contribution you are talking about is at the order Q to the power D plus 1. So it's at a higher order in Q,
I see.
Which I'm not able to capture here.
Okay, then suppose, say for example, if I don't consider free fermion, but I consider, for example, in 2D, nu equals 1/3 Laughlin state, and that's an insulator, and I try to calculate this accumulance of this charge. So because I don't have a metal, so you will say that will you expect that the leading order term will tell me something about the say the Hall coefficient?
No, or I should say I don't know. I don't know whether there will be a variation of what I'm talking about here that is capable of, say, probing the Fielding fraction nu, or any information about the topological order.
The reason why I ask is that for quantum Hall, for these Laughlin state, the wave function is known, and the algebra of the density operator is also known. So the state is known. So I think you can also calculate this function and right, and supposedly that will relate to this multipartite entanglement entropy that you're mentioning.
Yeah, I think what you said is right. I think what you said is reasonable. I'm not sure what the result would be, but I think it's interesting to think about that. It's very interesting to think about that. I noticed that recently on arXiv, I think there's a paper that talk about charge fluctuations in quantum Hall states, in fractional quantum Hall states actually, and there they talk about higher order qubits, which is in some sense related to what I'm talking about here, because I want to talk about higher order qubits too. But for them, it's more about bipartite fluctuation. So the paper that I had in mind, I don't recall the name of the authors, but I think it's a very recent paper that talk about higher order qubits of charge fluctuations and apply it to fractional quantum Hall system. But then I think there they talk about bipartite fluctuation. in the following, you're going to see that I'm not going to talk about bipartite fluctuations. I want to talk about multipartite fluctuations. Because if you look at bipartite fluctuations for gapless systems, and actually for, I think even for gap systems, it will also in general have an area law contribution that I don't want. I want to subtract them out, and so that forces me to think about multipartite cumulants. So I will show you. So basically, the multipartite cumulants is basically this one that I'm going to show you here. So QA, QB, QC. So for 2D, I have 3 regions. I want to look at this connected correlation functions of number operators in these 3 respective regions. My results in the previous slides would translate into this result. When you do the Fourier transform to real space and integrate over the respective real space, you will get this log divergence with a coefficients that probe the Fermi C topology. So I noticed that people have been trying to use higher order cumulants to characterize even topological order. I don't have anything that I'm confident to and conclusive to tell you here. Yeah, maybe we can chat more about it, and if you're interested, maybe we can look at that paper together and see what comes out when one talk about multipartite number fluctuation. Because I think in that paper, in recent works that I'm aware of, even though they're talking about higher order cumulants, they were not looking at the multipartite charge fluctuations. I think in the paper that I have in mind, they're talking about corner contributions of some higher order cumulants. And that is a little bit different from, it's quite different from what I'm focusing on here. I think on the general picture is that, I think you're right. The general picture is that some topological information is actually encapsulated also in higher order cumulants of charge fluctuations.
I see. Thank you.
You're welcome. Thanks for the question.
Do you mind to explain, Pok Man, this the log higher power? That means log taking several times. Right?
Thank you for asking this. Not that. If it's that, then it will be too boring, because log, it will be very, very small.
Right.
It is log, 1 log, but raised to power 3. Yeah. So it is like when you say sine squared, you're not taking sine twice, but you're calculating sine and take that answer and raise to power 2. So I'm using that kind of notation. But I also realize that when it involves log, it may be a little bit confusing. So not taking log 3 times, but take log once, but raise it to the power 3.
So it will be log lambda bracket to the power 3.
Yeah, log lambda raised to power 3. I think that will be maybe a less confusing notation. Yeah, and that is what our result is about. Yeah. Thanks for that.
Can you remind us what lambda is?
Yeah. Oh, yeah. So lambda, it's the dimensionless linear system size. So it's basically L over A. Lambda is a dimensionless quantity that characterizes the size of the system. L is the linear system size. A is some microscopic UE cutoff. Okay, so in 1 dimensions, I assume that there is an additive non-universal constant, right? Yes, exactly. Yeah, I agree. Yeah. And in higher dimensions, is there an additive non-universal constant, which is a lower power of log? So the results I'm showing here is the leading order divergence. So in principle, not in principle, I think practically, in reality, there are some subleading corrections. I'm not sure whether the subleading corrections will have log squared, for example, in 3D. Oh, okay. Let me put it this way. There will be. Yeah, there will be, because when you look at this lambda as some A, you will have some log square part when you change your UV cut of little a by, say, a factor of 2 or a factor of 3. So there will be generally some log square contribution or log contribution, but their coefficient is not universal. The leading divergence is log cube, and the coefficient of that leading divergence is universal. I hope that is that clear, Professor? Yeah. So based on my previous results on the density correlation, and I'd like to again stay on this page for just a little longer, because maybe that is something that is measurable, and maybe it's more measurable than what I'm going to talk about next. Maybe not, probably not in a real metal, because it's hard to know where the electrons are sitting at any instant in time. But with a cold atom microscopy, presumably you can take a snapshot and know where the fermionic cold atoms are sitting at any instant in time. And then maybe you can extract some density correlations. And this one, I think it's also similar. If you can take a snapshot of your cold fermionic atomic gas and try to count the number of particles in respective regions and calculate a correlation out of it, and look at how it changes the linear system size lambda, maybe you can find a logarithmic scaling, really experimentally observe a logarithmic scaling. And our prediction is that the coefficient of the logarithmic scaling probes the topology of your cold fermionic Fermi gas topology. The Fermi sea of that, topology of the Fermi sea of that cold atomic gas.
Sorry for being so slow. What exactly is Q?
Oh yeah. So Q. Sorry, I now I recall I probably didn't really ever tell you what Q is. Capital Q is the number of particles in region A. That is Q. So it's C dagger C summed over all sites in region A.
Okay, so the answer in the end is divergent, or what? Well,
the answer in the end would diverge with the system size in this way that we predicted.
Okay.
Yeah. So yeah. And yeah, Q, or if some of you like, I can replace Q by N. That will be clearer that this is the number operator in a specific subregion.
Okay.
And for 3D system, I want to cut my system into 4 regions that I label as A, B, C, D. And if I look at this connected correlation of this number operators in this 4 respective regions that all meet at a point, that would not have any boundary area law contributions. It actually would have a logarithmic finite size scaling. It diverges with the system size in this logarithmic manner with a coefficient that probes the Fermi sea topology in the D-dimensional metal. Yeah. And so we can summarize, okay, generally, we actually didn't prove this rigorously for general dimension. We have results for 1D, 2D, and 3D, which you can prove rigorously. And it seems to organize in this following nice form. But I can't bet that e equals to 4, it will still look like this. So
so maybe one question, Pok Man.
Yeah, hi, Inji.
Hi, how are you? So how do you put, for example, these regions in a torus in 3D, or how is there a finite size regulation for the regularization for the entire system size? Is it like a torus or?
Okay, so of course, if I want to talk about translation invariance, then my system has to be on a torus. But let me imagine that my system is really, really, really very, very large. Then whether I put periodic boundary conditions shouldn't really affect the physical properties if I just look at a rather local restricted region in my metal, which has still a pretty large system size, which I call L, or L divided by A is lambda. That is what I call lambda. So if you cut, so I don't really need to care so much about what is really happening way outside. So here I have a restricted region in the metal that has a size L, and outside I will still have my metal. But these properties, to calculate these properties, I can pretend that I have full translation invariance and calculate and do a calculation that I know how to calculate and get an answer which I believe is true, as long as my system size is not too big to know about all the details of the boundary. And actually, when we do a numerical calculation, we do have an open boundary conditions, and we still see pretty good matching with our results, which is derived when we assume we have full translation invariance. In which case, the boundary effects is neglected. Or to put it another way, as you said, we have a periodic boundary condition. When we do a numerical when we do an analytic calculation, we assume we have full translation invariance with periodic boundary conditions on the metal. But when we do numerical calculation,
but
we
suppose
actually
this, let's take, for example, this 2D metal case. So why is there not a contribution to the fluctuations from the bound? Let's say your region is this circle. Why is there no contribution to the fluctuations from the boundary of that and the remainder of the system, let's say, the circle?
Okay. Yeah, so because in a sense, this quantity is characterizing the mutual entanglement between all three regions, and they all meet at a point. So these places actually would not contribute to the entanglement that care about. It requires the electron to go through all these three regions. So it's really an information about this point, and I think it's one of the ways to see why we can probe the topology. Something robust instead of something that is geometrical and it depends boundary geometry.
Okay, I see.
Yeah,
very good.
Yeah.
Thank you.
Okay. So based on what I can come back to what Inti said on the next slide actually. So while I draw this ABC in this draw this region in this style I label ABC, I can actually have a region outside that I call D. But that is not what I'm interested in. I can have a region outside that I call D. That wouldn't affect the results that I have shown here. Yeah, Julian.
Yes, let me make sure. So earlier in this 1 plus 1D maybe Cardi formula of the 2 plus 1D, this topological entanglement entropy Lavin-1 or Prescale.
Yes.
Those are the virtual card in the real space, right? And just remind me again, did you switch to the momentum space card at some point?
No, I'm always cutting things in real space. So all these figures I'm showing you here are real space figures.
Right. Okay.
Yeah.
But maybe in the previous slide. I think
here this is momentum space.
Right. So So
because here I'm showing you a Fermi C, and I'm doing an integral in momentum space. So, and on this slide, there's nothing about real space at all. On this slide, everything I'm calculating are defined in a momentum space. These are density correlations at some certain momentum wave vector. But with this result established, and I'm drawing all the pictures in momentum space and establishing this result, then I can do a Fourier transform and talk about the real space density correlation. And then I can integrate over the respective regions in real space and get, say, QAQB or QAQB QCQD connected correlation function.
Okay.
Yeah. And they will be proportional to chi-f, at least the leading order. This result, I've tried to be more careful about this and to stress that it is true when Q is small enough. Of course, you can object that when I do a Fourier transform, I have to involve all Qs, even large Qs, but they are not going to affect that much in the thermodynamic limit. If I want to talk about, the finite size scaling when the size is really, really large, then the leading divergence should be sensitive only to the small Q behavior in momentum space. So I'm using that result for small Q in momentum space and give you a result of the finite size scaling in real space. That gives you the leading divergence, which takes the form of log raised to some power with a coefficient that is proportional to chi-f.
Okay, thanks.
Thank you. So
do you think it's also possible to do some kind of a virtual card in the momentum space? I'm not sure where you will extract anything, but in case you, because for the Fermi surface, this boundary that I'm not sure he extract anything, but I just asked in case.
Yeah, I think this is an interesting question. I also recall another paper. I think it's from a Boston group. At Boston, you're in Boston, but when I say Boston group, I'm in Boston University group. I forgot who is the exact author. But they actually also studied bipartitioning in momentum space and look at the entanglement entropy from which they can actually extract the Landau parameters that characterize the Fermi liquid interaction. So I think there's some interesting work about doing partitioning in momentum space, but they're not able to extract the topology of the Fermi sea. So here what we're doing is to do a partitioning in real space, and miraculously we can actually probe the topology of Fermi sea that lives in the momentum space.
Okay,
Yeah.
thanks.
Yeah. So okay, thank you, Juven, for your question. So let me move on and now talk about the same thing from the quantum information perspective. So now, a few slides ago, I motivated us to calculate this horrible looking combinations of entanglement entropy. It is horrible looking, but it's actually quite well motivated because Kitaev-Preskill, Levin-Wen taught us that if you consider this kind of combinations, then you can cancel out the real, the area law, the boundary law contributions. So for 3 dimension, when we have 4 parties in real space, let us also consider a combination that cancels out all the area law contributions. And even, not just the area, but also, this volume of the line, this will also contribute to entanglement entropy. In this combination of entanglement entropies, all those contributions that could, in principle, depends on geometry and microscopic details that all canceled out, leaving only basically a point contribution that reflects the intrinsic correlation among all 4 regions, which meet at this point. Now, let us use this relation between entanglement entropy and charge fluctuations, combined with this god-awful combination of entanglement entropy. A simple algebra will show you that this I4 actually equals to this QAQBQCQD kinetic correlation with ... plus ... So this is not really exactly true. There will be some higher order cumulants, but they can be shown to be small. This guy, QAQBQCQD, kinetic correlation function, grows the fastest in terms of changing the system size. It has leading divergence in the thermodynamic large system size limit. So combining this formula with our previous results that show you how the multipartite number correlation scale with the system size, we can show that the mutual information also has a similar scaling with the system size, which also have a universal coefficient that probes the Fermi sea topology. That is for d equals to 3, and you may ask, what happens to d equals to 2? So d equals to 2 is a little bit, let me see how I'm doing with time. Oh, it's actually, okay. Okay, maybe I have to speed up a little bit. I hope you bear with me. So for d equals to 2, it's a little bit trickier because the entanglement entropy only depends on even order cumulants. What we know about 2D is that you need a odd order cumulant in order to probe the Fermi sea topology. So that poses a question. What we realized is that if you modify the definition of entanglement entropy a little bit to what we call the charge-weighted entanglement entropy, and I think it's related to something that is named in a similar way and introduced in 2016 by this group of people in order to classify SPT phases. So I think they were motivated by the following thing. So the Kitaev-Preskill formula, Levin-Wen formula, use entanglement entropy to probe topological order. In SPT phases, you don't have topological order, but there's still some sense of topology in it. And they ask the question, what kind of entanglement entropy, modified version of entanglement entropy, can probe the features of SPT phases? So there they introduced the term of the idea of charged topological entanglement entropy. What we're introducing here is similar to that. So basically, we modify this definition of entanglement entropy by sticking in a factor of charge fluctuation. So again, Q is the charge operator or the number operator that counts the number of electrons in region A. So this is QA is the operator minus the expectation value of it. Then this is the factor that we'd like to stick in to modify the definition of entanglement entropy. In this case, you can show that this charged weighted entanglement entropy would be related to the odd cumulants of charge fluctuation. And then when you consider this tripartite mutual information of this charge weighted entanglement entropy, it's actually proportional to QAQBQC kinetic correlation function. So it has a log square divergence, just as this third order cumulant would have a log square divergence, whose coefficient is proportional to the topology of the 2D Fermi sea. In 2D, we can do numerical calculations for non-interacting fermions. So entanglement entropy, or the charge-weighted version of it, can be calculated effectively, actually, using the 2-point correlation function. So Ci dagger Cj, this is the 2-point correlation function. where ij are sites strictly in region A. With this, we can define this correlation matrix that can be in turn related to the entanglement entropy. So you can calculate the entanglement entropy without invoking the reduced density matrix, which is exponentially large. You can actually relate it to a much smaller correlation matrix, which is only linearly large in system size. So with this, we can calculate the charge-weighted mutual information. I did it for both tight binding model for triangular lattice and square lattice. They have different ways of partitioning. And relating to what Inti asked a moment ago, we actually implement this for open boundary conditions. And we can actually show that we actually see numerically that the boundary doesn't matter so much. Overall, it still obeys this log square divergence, which we derive by ignoring the presence of boundary, by assuming the full translation invariance. We can actually see this log square divergence, log squared scaling of the tripartite charge-weighted mutual information, and we can extract the coefficients, which you see, for example, depending on whether you have an electron pocket or a hole pocket, the way that the parabola scale actually a curve actually changes sign, and actually also I think going back to the question that I think one of the audience asked from the very beginning, what happens when you just change the chemical potential a little bit, and which would amount to changing the size of a Fermi surface. So we do it. We did this. So we change the chemical potential, which amounts to changing the size of the electron pocket or your hole pocket, changing the size of the Fermi C. It doesn't really change the tripartite mutual information, which you used to characterize the topology of the Fermi C. And so that matches pretty well with our analytic prediction. With this result, you can also use it to probe a Lifshitz transition. So let me fix at one system size, a rather large system size, say 150 by 150. Then if you take a ratio of your tripartite mutual information, then for large enough system size, this ratio should be proportional to a quantized ratio. So if you compare two systems with two different types of Fermi C topology, then this ratio of tripartite mutual information should be equal to the ratio of the respective Fermi C topology. So if you look at the triangular lattice and you tune the chemical potential to go through a Lifshitz transition from having a one electron pocket to two hole pockets, you can actually see that this ratio changes from 1 to -2. So a reference mutual information is calculated for the case when you have one electron pocket. So when the chemical potential is negative, you have one electron pocket, that ratio gives you 1. But when you go through a Lifshitz transition, you get to another plateau where this ratio becomes -2, because now you have two hole pockets. So allow me just for a second, flash through this picture. It looks quite, in some sense, in some spirit, similar to what von Klitzing measured for integer quantum Hall, but that is really an experiment. What we did here is numerics. So it's a little bit presumptuous for me to make this comparison, but I still nevertheless want to show you that at least there's some numerical observable that actually shows a plateau transition, indicating the change of the topology of the Fermi C, which is similar in spirit to what people have studied in gap topological phases, when you have some measurable quantities like Hall conductance, which also go through some plateau transition when the topological phases change. But again, Jed, yes, Jed raised your hand, so please speak up.
Hi, Pok Man, nice to see you.
Hi.
So you mentioned numerical calculations, and I think here you the cases you studied are free fermion case. So
Yeah.
do you have any comment about interacting systems and whether your formula has a huge numerical cost or reasonable cost for interacting system, like the simplest interacting system in 2D? Yeah, I think 1D is doable. Yeah, in 2D. Yeah.
Yeah. So I don't have too much to say about this, but I think okay. So for 2D, I hope maybe someone can try to use, say, quantum Monte Carlo, or maybe some tensor network calculation mirror maybe to do a calculation for 2D. And I think, as far as I get it, I think it's easier to do this calculation for not for von Neumann entanglement entropy, but for maybe second or third Rayleigh entropy. Let me just very quickly maybe go to the very last slide. For example, here, so for what I told you, it's about von Neumann. We also have a similar result for Rayleigh entropy, and that is probably easier to probe numerically. I don't have an estimation of how hard that would be, or how much cost it would be, but that is probably easier to probe numerically, Rayleigh entropies, and we do have results for the Rayleigh entropies. So without taking the n goes to 1 replica limit, and for free fermions, we can establish this results. For interacting system, we don't know whether this coefficient would be renormalized. But if we take the n goes to 1 replica limit and really talk about von Neumann entanglement entropies and the mutual information built from the von Neumann entanglement entropies, then we can actually establish that the coefficient is robust under Fermi liquid interaction. So we're actually in a little bit of awkward situation. So we have a conclusive statement for the interacting case in 3D. If you talk about the von Neumann 4-partite mutual information, then we know it is robust under Fermi liquid interaction. But that is not the easiest thing to probe numerically. Easier things to probe would be the Rayleigh entropies, and we don't know whether, from the analytical perspective, we don't know how it will be normalized by interactions. But if it is something that is practical to calculate, then I would encourage people to try to calculate it in I don't know, maybe 3D and see how it get renormalizes, or maybe in 2D also how it get renormalizes. It would be interesting to see, but I don't have anything conclusive to say in terms of the numerics.
Yeah, thank you. So you mentioned the quantum Monte Carlo and tensor network. How about exact diagonalizations?
That would be, I think that is probably very difficult because, okay, so let me show this. For free fermion system, L, the linear system size, can go up to 300. And I think I actually need to go up to about from maybe 50 to 300 in order to have a pretty good fit to fit the log square, because what we predict is some log raised to some power, that kind of scaling. If you do exact diagonalization, then I think you're heavily limited by a system size. So I heavily doubt whether you would be able to do a log square fitting and get some estimation of the coefficients in front of it. So that is my impression.
Okay, thank you very much.
Yeah. Thank you. It's really for free fermion system that we can try to stretch the system a little bit to allow us to have some idea of how the finite system scaling would be and to extract a coefficient for the log.
I see. Thank you.
Yeah. Thank you. So here I talk about, I try to make a comparison between experiments, which may be too presumptuous. Let me next talk about a real experiment that can hopefully probe the Fermi C topology. And that is introduced in our very recent work.
Sorry,
is
Lifshitz transition here important? These are meant to be the scaling of energy and the momentum, e to the k square, omega to the k square. Is that what you try to? Is that something you want to emphasize, or it's not? Just some quantum vector.
I would say Lifshitz transition here on this slide only mean that the topology of the Fermi C changes. So that corresponds to changing your chemical potential such that it crosses one of the critical points in your energy dispersion. So the Fermi C topology changes, and I think quite commonly people would call it Lifshitz transition. So
Okay.
I'm not implying anything further than that.
I see.
Aside from saying that you have a topological transition, namely the shape of your Fermi C changes in a topological manner, and that can be probed using this quantum information measure that we're introducing here.
You did not mean to say omega scales like k square here.
I didn't mean to say that. Yeah, I didn't mean to say that. Yeah. So so in the second part, which wouldn't take too long, thanks for bearing with me, is to try to use an experiment, real experiment, to try to probe chi-f for d equals to 2. So let me just very quickly revisit Euler characteristic, because I want to relate the Euler characteristic for the Fermi C to the geometry of the Fermi surface. By that, I don't really mean Gauss-Bonnet theorem. Currently, we don't have a relation between the Gauss, using the Gauss-Bonnet to probe the Fermi C topology, but we have something in similar spirit. So if you look at a Fermi surface geometry, you can actually label some points to be critical points on the Fermi surface. And this is not the same critical points I'm talking about when I talk about the energy dispersion. So these are the critical points on the Fermi surface. For example, if I set up my coordinates in momentum space like this, I can define my critical points to be the one that has y velocity equals to 0. So these points, all these points I'm labeled either in red and blue, open or closed, these are the points where the Fermi velocity has a vanishing y component. But there are two types of these critical points. One I would call convex, like this one, and this one, the one labeled in red, will be called convex critical points. These are the points where, around these points, you can see that your Fermi C looks like an electron pocket. And around these points that are labeled blue, I call it concave critical points. These are the places where you increase y, or Vy go from positive to negative. Okay, but that is just the details. It should be quite clear from the picture what I mean by convex and concave. For the concave point, I will label as blue, and in the neighborhood of the concave points, you can see that the Fermi C environment actually looks like a whole pocket. So if I count the number of convex and concave critical points respectively, and turns out, let me just use half of them. I would like to focus on the one with positive x velocity. So here I label closed and circle to be one with positive x velocity, one with negative x velocity. I'm going to just make use of one of them. So let me focus on the solid circles. Those are the ones with positive x velocities. And there are two types of them, convex and concave. If I count the number of these respective critical points and take the difference, that difference would give me the Euler characteristic of the Fermi C. Okay. We established this rigorously in our archive preprint, but let me here just demonstrate to you with an example how this can be true. So for example, with these three examples here, you can see that CE is 1, CH equals 0, so the Euler characteristic is +1. Okay. For the whole pocket, you get -1 because CE is 0, but CH is +1. For this annulus Fermi C, you have equal number of concave and convex critical points, so the Euler characteristic is 0. This annulus Fermi C actually has the same topology as a circle, and we know that a circle has an Euler characteristic equals to 0. So everything makes sense here. And if you deform, for example, let me look at the electron pocket again. You can deform it smoothly like this, and then try to pinch it a little bit. Then you create 2 convex critical points and 1 concave critical point. The difference is still 1. So it's plausible, I hope, to you that this difference actually counts the Euler characteristic of the Fermi C. And we're going to make use of this. Since we want to probe the Euler characteristic of the Fermi C, and we can relate it to the properties of the critical points, we are going to look for a physical phenomena that is sensitive to the critical point. And in fact, not just to the number of critical points, but also should be sensitive to whether that critical point is convex or concave. To do that, let me just put down a metal that I want to study. It's a 2-dimensional electron gas that I want to study. And on the right, I draw the corresponding Fermi C. And for simplicity, let me look at it as an electron pocket. Okay. In order to probe this, to probe the topology of Fermi C, let me lay down 2 superconductors, so proximatize my normal metal with 2 superconductors with a pi phase difference. And I want to consider a planar Josephson junction. So deep inside the junction, basically I have translation invariance in the x direction. And because I have translation invariance in the x direction, deep inside the junction, I can label my states with a quantum number, kx. So here is my Fermi C. And if I look at this kx, I can linearize my dispersion near the Fermi surface. Then the BDG Hamiltonian that describes this junction would just take this form. Okay, so tau z and tau y are the Pauli matrices acting on the particle hole space. Here I'm writing down the BDG Hamiltonian. The kinetic term is linear because I linearized the dispersion around the Fermi surface. And this tau y is the pairing term. It switches sign depending on whether y is positive and y is negative, because I have a pi junction. So when y is larger than 0, I have a superconductor with phase 0, and for y smaller than 0, I have a superconductor with phase pi. So the superconducting pairing term, which acts like a mass term in the Dirac Hamiltonian, actually changes sign. And this actually is just a very familiar form. It's a Dirac Hamiltonian with a mass term that changes sign, so we know that has to be a Jakob-Rabi zero mode for each kx. Value of kx. Oh, sorry. Okay. Can anyone still hear me? Oh.
Yes, but there's confusion, but they still can hear you.
Okay, because my AirPod runs out of battery. I'm sorry, but now I'm just using the speaker. Juven, if you can still hear me clearly, that would be great. So I will just keep proceeding. I'll finish very soon. The thing I want to say is that if you put your kx here, you will still have a Jakob-Rabi zero mode. So basically, for each kx, you will have a Jakob-Rabi zero mode. These are the zero energy Andreev bound states that's very well known to exist in a pi junction. But the point I want to emphasize is that if you consider kx that is very close to the critical points, then you can no longer linearize around the Fermi surface. Actually, at the critical point in the y direction, your dispersion is really parabolic-like. It's quadratic-like. You can no longer linearize at the bottom of the parabola, right? So the kinetic term should no longer be approximated as this linear in momentum way. And so close to the critical point, you shouldn't expect to have a Jakob-Rabi zero mode. Your Andreev bound state would no longer be at zero energy for any momentum kx that is close to the critical point. And in fact, if your kx is way outside the Fermi pockets, then you should have a very high energy states that the superconducting pairing gap shouldn't play a significant role at all. So your energy should be it's just like a normal band dispersion. So inside of Fermi pockets, you will have zero energy Andreev states. Outside, you don't. So generally, there will be a dispersion. Your Andreev bound state will have your energy actually depends on kx. And that dispersion actually happens very drastically near the critical points on any critical points on the Fermi surface. So you can do a specific calculation for, say, if you go to the environment or neighborhood of a convex critical point whose Fermi C environment is electron-like, then you can solve for the energy spectrum of the Andreev states. This is what you will find. This is what you will find. So here I've chosen W. W is the width of my junction, the separation of two SN interfaces. I've chosen it to be some small. You can actually choose to be 0. You get the same, basically the same shape. Basically, for very short, narrow junction, you will have one Andreev state per critical point. The key thing, again, is that when you are very deep inside the Fermi pockets, your energy is basically 0, because, again, the Andreev state is basically Jakob-Rabi zero mode. Close to the critical points, you will have drastic dispersion, and away, far outside the Fermi pockets, your energy actually, the energy of the Andreev bound state actually would approach the bulk normal band edge. And this gray shaded region corresponds to the bulk continuum states. So there's dispersion of the Andreev states. And another point that I would like to call attention to is that my lines here, the dispersion line here is also colored. The color scale has the following meaning. If it is blue, then it means the wave function is predominantly hole-like. If it is red, then it means the wave function is predominantly particle-like. So you can see that if you have a rather high energy Andreev states that is close to the band edge, then if you do this near a convex critical point, then your Andreev state is actually basically is an electron. If you're deep inside the Fermi pockets, then right, you are a superposition of electron and holes. If you're 0 energy Andreev states, then it looks green because it's an equal superposition of electron and holes. But if you have high energy, then your Andreev state is predominantly an electron or a hole, depending on whether you are doing this analysis near a critical point that is convex or concave. And now let me talk about the following thing. So because you have a dispersion of Andreev states, if you're an Andreev states inside a junction, you actually move.
when you move, you eventually move outside the junction. So let us see what is the fate of this Andreev states. So let me focus, say, on a state, so with 0.5 energy. If I am inside a junction, then my W is rather small. So this is a state which is not equal, but it's still a significant superposition between particles and holes, and that's why it looks orange or yellow. So it has both particle and hole components. But as you increase W, you can see that it will change into a state that is predominantly electron, or it will change to a state that is predominantly a hole, depending on the local environments of the Fermi surface. So if I inject, so if you are an Andreev states here, you'll move out, and if you have some numbers of convex critical points on the Fermi surface, then this Andreev state would turn into an electron definitively. If you look at this picture, when you move out of the junction, you can think about it as increasing the junction size gradually. So you're increasing W gradually. Then your state, the Andreev states, will go from being orange and slowly into red. So if you're near a critical point, a convex critical point, and you think about an Andreev state associated to that convex critical point, inside a junction, you have an Andreev state. When you move outside a junction, you will turn definitively into an electron. On the other hand, if you have a concave critical point, such as when you have a hole-like Fermi pockets, you have a concave critical point, then the dispersive Andreev states would move along the junction, and when it exits the junction, it would turn into a definitive hole. So using this relation between the transport properties of Andreev states and the convex concave properties of the Fermi surface, you can actually get a rectification effect or do a transport measurement that has a very interesting IV characteristic curve. So let me now look at this setup, and I have lead 1 and lead 2. I'm going to bias the voltage in lead 1 and measure the current that flows into lead 2. When I increase the chemical potential in lead 1, I'm injecting electrons into the junction. Then depending on how many convex critical points I have, which is labeled by CE, then I will have some number of electrons that can perfectly go through. I'm assuming ballistic transport here again. Then I will have CE number of electrons that can go through. And so you will see when V is positive, or when you have positive chemical potential, you will have an IV curve that basically look like this, with a slope that is determined by CE, the number of convex critical points that you have on the Fermi surface. Now, when you bias your voltage such that in lead 1 you have a negative chemical potential, in this way you are injecting hole excitations into the junction. Depending on how many numbers of concave critical points you have on the Fermi surface, then you will have CH number of holes that can pass through the junction and be collected on the other side in lead 2 as some currents. So you can see that when you have a negative bias voltage, then you have an IV characteristic curve in this negative bias region, which has a slope determined by CH, the number of concave critical points on the Fermi surface. So generically, if you look at a Fermi C with a generic shape, then the IV curve, the I2 V1 characteristic curve, would have a slope in the positive region, positive bias region, that is different from the slope in the negative biased region. The respective slopes is determined by CE and CH. Now, this number CE and CH, you can say it depends on how I, arrange my coordinates. So if I depending on how I arrange my junction, the counting of CE and CH might be different. So in this case, when I have a circular Fermi surface, you can't really appreciate that. But if you have a more weirdly shaped Fermi surface, then you will see that depending on how I arrange my junction, CE and CH could take different integer values. But nevertheless, no matter how you orient your junction, and no matter how the Fermi surface is shaped, CE minus CH is going to be a topological number. It only depends on the topology of the Fermi C. That number can be probed by just looking at the IV characteristic and comparing the difference between the slopes in the positive and negative bias region. Or you can apply a AC voltage pulse in V1, in lead 1, and try to measure a direct current in lead 2, which would have a size, a magnitude, that depends on chi f. which is the difference of convex and concave critical points. So basically, with this setup, we predict a rectification effect. You have an AC current in lead 1. You have an AC voltage applied to lead 1, and you're going to pick up a direct current in lead 2. The amount of direct net current you pick up in lead 2 is proportional to the Fermi C topology in the 2D normal metal. Now, with that, I would like to, I know I've overrun, and I'd like to just conclude here with some interesting results that we found. In the future, I hope, so what we talked about here is mostly about, it's actually all about non-interacting fermions. But actually in our paper, in our paper with Martin and also Charlie, we discussed Fermi liquid interaction. For 2D results, we found that Fermi liquid interaction would renormalize the coefficient. For 3D, we can actually do a perturbative calculation and show that if you only look at the RPA bubbles, they do not renormalize the coefficients in front of the log for 3D if you calculate this 4-partite mutual information. So we have tried to consider some interaction effects, but what happens if the interaction is so very strong that it's not even a Fermi liquids? In non-Fermi liquids, you still have a Fermi surface, and you can still talk about Fermi surface topology. Would any of the tool that we introduce here be helpful, or would some other tools that would be helpful in characterizing the topology in non-Fermi liquids? These are some open questions that I feel very excited in exploring. With that, I would like to end here. Thank you very much, Juven, for providing me with this opportunity, and thank you for many audience for asking great questions.
And thank you, Pok Man, for the wonderful, great talk.
Thank you.
Question from the audience. Amok, if I pronounce
Yep.
please.
Thank you for the talk. Maybe this is a bit of a naive question, but what is the topological quantum field theory that would actually go ahead and compute this chi sub f? Like, how is there any ideas you have regarding how to derive such a topological quantum field theory?
I'm not sure whether we can use a TQFT to describe a Fermi liquid or metal. At least in my most naive understanding, we use TQFT to describe some gapped phases like topological orders. For metal, I don't know, but maybe someone can say, maybe from a holographic perspective, maybe you can have a high dimensional bulk described by a TQFT, and then on the boundary you can have a Fermi liquids, and then maybe using the bulk TQFT you can calculate the chi f for your boundary, Fermi C topology. That would sound very interesting to me, but also it's just a crazy guess. I don't know how that could be done. I have not thought about how that might be related to TQFT. Just at the first sight, I don't know how to make that connection.
Right, and maybe a related question. So I'm seeing here that the formula for the d+1 point density correlator, it seems to have the form of a differential D form. I guess if the momenta Q are taken to be infinitesimal.
Yeah.
So if that's true, what does that form actually represent? Is it some sort of characteristic class, or am I just overthinking that?
I would like to think that there is a relation, but if it is a differential D form, then it's probably not quite like the absolute magnitude of a determinant, but more like a determinant. So maybe there's also a subtle difference between what I have here and a differential form, because when you have a differential form, then you really have a determinant without an absolute magnitude. Roughly speaking, I would say that. So I don't know whether there is a more geometrical interpretation or differential geometrical interpretation of the results that I have here. I have to be very honest with you. We found this very amusing or amazing results, but we don't think we have a deep enough understanding of why this is true. We can demonstrate that this is true, but maybe there's a deeper reason for why this is true, and we haven't completely satisfied ourselves yet.
Thank you.
Thank you for your question.
Any other questions, comments?
I think someone's trying to write his or her question. I saw this in the chat box.
Yes.
So I can totally wait. Yeah.
At the same time, if someone want to ask question directly, feel free.
Yeah. Yeah. I have time. I don't know whether Juven, you need to go somewhere. Sorry for overrunning. I didn't expect it to take 2 hours. Oh, maybe right. Okay.
Hello.
Yeah, we can hear you.
There is a question about the paper of multipartite entanglement entropy. In the last part of the paper, you consider the interaction by perturbation before you have analyzed the dimension of different term and only consider the leading term of the contribution of the entropy. But after including the interaction, you have assumed that the dimension or level of the diagram are not affected by the interaction contribution. Just like some diagram in the paper. But for example, for 1D case, the interaction have 4 Fermion operators, which can be naively seen as 2 operators like Q square, which may seem change or lower the dimension of the diagram, which means that we should consider other terms which has the same level as before. So I think maybe we should not consider the diagram with 4 Q operators, just like in figure A for 3D case.
When you talk about dimension of the diagram, do you mean
or level, just like L for 3D, we have L square. For 3D, we have log L.
Yeah, log to the power 3 in 3D.
Yeah.
Yeah.
But I think for the diagram, if we have 4 Q operator and 1 interaction vertex, we may have different behavior of the L, which may be different or have lower level of the, or which may decrease just like 1 over L or some other.
So here I think we only need to think about diagrams that look like this instead of coming up with other vertices or other structure of diagrams, because, and that's quite different from 1D, because I think from 2D and 3D in high dimensions, we really have a Fermi liquids instead of a Luttinger liquids. And in Fermi liquids, if you run the RG flow and be content with low energy description, then the only non-irrelevant interactions are these bubble diagrams, right? These forward scattering interactions. And that's why we try to analyze what happens when you include and just include this bubble diagrams, this forward scattering, and see how that would change each individual diagram that we have calculated for the non-interacting case. And these RPA diagrams generally would change the answer if you calculate the nth entanglement and nth Rayleigh entanglement entropy. But if you take the n goes to 1 limit, I'm trying to motivate it here. So these are maybe some complicated results, but the thing is that when you take the n goes to 1 limit, these contributions from the diagrams actually vanishes. And we only join those diagrams with RPA bubbles because we think these are the only interactions that would matter that would matter at low energy for Fermi liquids in 2D and 3D.
My question is that here you just consider like figure B or figure C, but is this the leading contribution of the entropy, or if there is any other diagram or terms which may have higher, which may be more leading for the contribution?
Right. So okay. So here I'm drawing this diagram for the Q to the power 4. So the 4th order Cuminance. For 2nd order Cuminance, for 6th order Cuminance, or even for for 6th order Cuminance, for 8th order Cuminance, you also draw similar diagrams, attaching these bubbles connected by this Landau parameters that describes how those are being corrected. So basically, we no longer have we no longer have the nice relation of relating entanglement entropy to just the Cuminance, because we are doing interacting fermions. But we can start from that and perturbatively add in these diagrams, these bubbles, and see how each term are getting modified. This is just demonstrated for Q to the power 4, but for other terms, you can also demonstrate them in a similar manner.
We have Q to the power 2.
For Q to the power 2,
because there is injection, we cannot may the contribution of this term not vanish, just like for the non-interaction case.
You can have Q squared, but the Q squared would anyway be canceled out when you calculate the multipartite mutual information.
And because it's for me not pretty aware they maybe I should check it.
Yeah. So I think for Q squared, you can also, so first of all, you can also draw this. So this is for Q4. For Q squared, you will also draw similar diagrams, which I think you will run into a similar problem that when you take n goes to 1, the interaction correction will be 0.
But if we have only Q to the power 2, we just have n minus 1, which may not vanish for we take the limit of n equals to 1.
Let me.
By the way, I think the discussion becomes long, so maybe we should thank Pok Man for a wonderful seminar first, and then people can still stay to discuss. But
that would be great. That would be great. Thank you. I'll still be here. Thank you.
Thank you.
So let me see.